Okay, so today, or for this lecture, we're going to start Lecture 2, Part 5. Discussion will concern continuity of a function. What is continuity? So, continuity of a function. Right? And so, continuity is the definition. A function f is continuous at a number a if we have the following result. The limit bear with me. If the limit as x approaches a of the function f of x is equal to f of a. Okay? So for continuity, if we take the limiting value a and plug it into the function and we get an output f of a, then we say that the function is continuous at a. Okay, so draw you a picture of a function that has such a property. Now, embedded in this definition is a limit. And so all of the structures that we learned about limits in the previous lectures on Chapter 2 are in play here. Okay, so that means when we look at this figure of a hypothetical function, okay, so here's a function that's continuous at x equals a. And you see, note very carefully the red arrows. Okay, so we are approaching a from the left, and we're approaching a from the right. So we're adhering to the formalities of the definition of the limit. And note that f of a is a solid fill, a solid red dot on the function f of x. So left and right limits are the same, and f of a is defined for the function. Okay, so that means, well, we've seen prior cases where there's a potential for f of a to be some, say, perhaps point up here. So we have this little gap right here, making it a jump discontinuity. Well, for continuity, this jump doesn't exist. Okay, we come at it this way, and we come at it this way, and we also happen to have the function existing defined for f of a. So in other words, f of a is equal to our L value from the previous notes. Okay, so f of a is equal to our limiting value. So if we have our f of a equal to L, now in this case, suppose for a moment that the function's output at x equals a was this dot up here, this point up here. Well, in this case, f of a is not equal to L, and so you can readily discern that the function is not continuous because of this gap. So that's the subtle point that's somewhat overlooked in the text. Okay. All right. So moving on. Implicit in this definition we have a couple of things to look out for. Number one, f of a is defined, as I just mentioned. That is, a is in the domain of f of x. Okay, as shown in the picture on the right. Another implicit notion is the limit as x approaches a of f of x exists. Right? And again, that's implicit in the illustration I've just shown. the limit as x approaches a of f of x is equal to some number. Okay? And another concept, the third principle that's implied in this definition, is the limit, this notion right here. Right here. The limit as x approaches a of f of x is equal to f of a. Okay, so that, again, that means that L and f of a are the same number. Okay, they have to be the same, where in previous examples they weren't always the same. All right, so let me show you some examples of exceptions to these three notions. Okay, so consider this illustration right here. Okay, so at x equals 1, rule 1 is violated. Okay, so right here we have a hole, and so a is not in the domain of f. Okay, f of 1 does not exist. So this graph violates rule 1. So it is not continuous at x equals 1. Okay, so no continuity because of the hole here. At x equals 3, what's going on at x equals 3? Well, we have this gap. So obviously we're not continuous here. And rule 2 is violated because the left limit, as we approach 3 from this direction, is clearly not the same as x approaches 3 from this side. So rule 2 is violated because this limit, x approaches a, doesn't exist. Namely because the left and right limits produce different results. All right? And then rule 5, I'm sorry, at x equals 5, rule 3 is violated because as we approach, the limit as x approaches 5 from either direction does not equal to the function at 5 because we have this gap right here. Okay, so that's what we have to keep in mind when we assess continuity of a function. All right, so let's do some examples. Paste an example on Smartboard. Okay, so consider these 4 examples. So the question being asked is, where are the following functions discontinuous? All right, so let's treat each one. So in case A, we have here drawn a rational function, and if we note carefully, it may be kind of hard to see in the smartboard, we have a hole right here. Okay, there's a hole right there. So if you were to use your graphing techniques from the Lecture 1 notes and graph this function, you would discover there's a hole at x equals 2, And so that's where the discontinuity is at for this function at x equals 2. All right. In the second case, for part B, f of x is a piecewise defined function, and this is an example of we note that the limit as x approaches 0 from either side would be infinity, but at x equals 0, we define the function piecewise to be 1. So in this case, the limit as x approaches 0 does not equal to the function at value at 0. Okay? And here's a case looking at part C. Same as part B, basically the function is not defined. Well, the limit as x approaches 2 does not exist. The limit doesn't exist, or the limit does not equal to the function value at x equals 2. So that is, the limit of this function as x approaches 2 does not equal to the function value at x equals 2. And then the part D is an interesting case. In this case, I believe we've mentioned this before, the greatest int function shown here in part D, we show that it is not continuous at integers because the left limit does not equal to the right limit for any integer, but the function is defined for all integers. So left and right limits for any integer doesn't exist, or are not equal. They do exist, but they're not equal. But the function is defined for all integers. Okay, so some interesting examples. All right, so as in the case with limits, we have what's considered to be left and right continuity. So let's see what that's all about. So with left continuity, we have the following. Left continuity. Right, and essentially we just reuse the definition of continuity, except instead of x approaching a, we approach a from the right. So we use the superscript plus for a. No, I'm sorry, we use the superscript minus since we're approaching it from the left. I said left, right? So let me change that. Left continuity means that we approach a from the left, which means from numbers less than a in the limit, and of course that has to equal to f of a. All right. And then conversely, right continuity, you can probably guess what the definition of right continuity is. We approach a from numbers bigger than a, so we'll use a superscript plus in our a value for the index of the limit operator. Plus, a plus, right? And so as you might guess, if a function is both left and right continuous at x equals a, then it's continuous at x equals a. All right, so let's do an example. Let's let f of x equal to the greatest int function. And let's analyze its left and right continuity. Okay, so we have this. So for any integer, let n be an integer. Any integer. Z is the set of integers. Okay, and so the limit as x approaches some integer from numbers bigger than the integer of f of x. Okay, well, that would just equal to the integer itself. Okay, and you can discern that from the graph. which is equal to f of n. Okay. Now, how about, so this would be the right limit. So let's consider the left limit as x approaches n for the greatest int function. Obviously, it won't be n. It'll be the first integer to the left of n. Okay, so that would be n minus 1. So you can see that the left and right limits are not the same, and because of that fact, the limit as x approaches n for the greatest int function doesn't exist. So if left and right continuity, if a function is not left nor right continuous, well, if the left continuous limit does not equal to the right continuous limit for the function, then the function is not continuous at that particular value, in this case n. All right, so pretty straightforward example. All right, so let's do another example. Suppose I give you a function f of x is equal to 1 minus the square root of 1 minus x squared. And I restrict it to, well, it is, the function is restricted, right? The domain of the function is negative 1 to 1. So show f of x. Now, instead of writing out the word continuous, I'm going to abbreviate continuous to the letter CTS. Okay, so we want to show f of x is continuous on the closed interval negative 1 to 1. Okay, and just for clarity's sake, CTS is the shortcut for continuous. Okay, I'm going to use a little bit of Twitter talk here. I'm limiting myself to so many characters. Continuous. All right, so CTS means continuous. So we want to show f of x is continuous on this interval. Okay, so all right, so before, well, I guess we can take a couple of approaches. Let me show you what one of the issues would be. Suppose we look at the graph. Consider the graph of this function, which is looks like this. Let me pull up the graph. Okay, so this is actually kind of a tricky problem. So, all right. So here's the graph of the function we're analyzing, continuity, and we want to show that it's continuous on the closed interval. Okay. So one of the things is consider the endpoints of the interval. What happens to the function at the endpoints? Do we have, well, let's just consider x equals 1. So the question is, do we have continuity at x equals 1 for this function? So, in other words, for continuity at the endpoint, at the outset you would think that the left limit, okay, as x approaches 1 from the left, does that equal to x approaches 1 from the right? And well, the function isn't defined for x greater than 1. So is there a dilemma here? Do we say that the function is not continuous at x equals 1? Well, there's a caveat here, and we say continuity we have a secondary notion, continuity at an endpoint. we need to explain what we mean by continuity at an endpoint. And of course, that means continuous from the right or continuous from the left. And I'll use CTS for continuous. So at x equals 1, f of x is left continuous. Okay? And since x equals 1 is an endpoint and it's left continuous at the endpoint, that doesn't pose a problem for continuity of the function, at least insofar as in a small neighborhood of 1. Okay, so the function is continuous. We will say the function f of x is continuous at x equals 1 by the fact that it's left continuous at x equals 1, and x equals 1 is an endpoint. All right, so continuing on with this assessment, it's actually kind of a proof situation. So if, say, we have this inequality, some number a is strictly greater than -1 and less than 1, okay, then use the limit laws. Okay, all right, so we have the limit as x approaches a, that's an a, f of x is equal to the limit as x approaches a. Okay, so we'll substitute in the value for f of x, which is 1 minus the square root of 1 minus x squared. Okay, and by the limit laws, we can distribute the limit operator term by term, since we're subtracting two functions. Okay, and so we know for this first term in the subtraction, the limit of a constant is a constant itself, so we'll have 1. And since a is restricted between -1 and 1, and so a is in the domain of the function we're taking, okay, we can take the limit operator inside the square root, because a is in the domain of the square root of 1 minus x squared. So pull that in. So that is, we can pull it in because a is in the domain of the square root of 1 minus x squared. And so using direct substitution, because what's inside the square root is a polynomial, so we have 1 minus the square root of 1 minus a squared, which is equal to f of a. Okay, so at least insofar as where a is on the open interval, okay, so where a is on the open interval, -1 to 1, we have the limit as x approaches a of f of x is equal to f of a, which conforms to our definition of continuity. Then we combine this information with the fact that the function is both left and right continuous at its endpoints. Combine those three pieces of information and we say that the function is continuous on the closed interval. A little bit tricky. Okay. So another example, we can examine the tangent function. Let me pull up a graph of the tan function. Okay, so let's see if I can get this to work. So consider this graph. Y equals tan x. So the question is, where is the tangent function discontinuous? Okay, well, look at where the vertical asymptotes occur. So if we consider, say, the vertical asymptote x equals -π². Well, we note that the limit as x approaches -π² from the left is positive infinity, and the limit as x approaches -π² from the right is negative infinity. So the left and right limits are not the same. So the limit as x approaches -π² of the tangent function does not exist, okay, because of the conflict. So the tangent function is discontinuous at -π², and it just so happens that the tangent function is discontinuous for all odd multiples of π². So we could say tan x is discontinuous at odd multiples of π². And the way we could rewrite that would be x such that x equals to, so an odd number is 2n plus 1 times pi over 2, where n is an integer. This is how we write n as an integer. N is a number from a set of integers. Okay, so that's where tan function is discontinuity. Okay, so a number of theorems I want to talk about without proof. I'll offer them up without proof, but we will use the results extensively. So let me grab those. Stand by. A couple of theorems here. All right, so what do we have here? So let's look at the first theoretic result. So if f and g are continuous at a and c is a constant, then the following functions are continuous. So the sum of the functions, the difference of the functions, the constants of the functions, the product and the quotient, provided that g of a is not equal to 0. So this almost follows from the limit theorems, right? The limit laws. So as a matter of fact, it is based on the limit laws. So if f and g are continuous, then so are the sums, differences, products, quotients, and multipliers. Okay. So let's go on to the next theorem. Any polynomial is continuous everywhere. All right, so we've already discussed that at length, I believe. So like any polynomial. So we know what a polynomial is. We've discussed its definition in the Lecture 1 notes. And of course, any rational function is continuous wherever it's defined. So it's continuous on its domain. Okay, so we talked at length about that. And the following types of functions are continuous at every numbers in their domains. So polynomials, rational functions, root functions, trig, inverse trig, exponentials, logarithms. Okay, so I think we understand that. We have a pretty good understanding of that. This is kind of a rehash of what we've been talking about. Another theorem, another final theorem, which is, I believe, more useful, and we'll see it a lot when we talk about derivatives of functions and integrals of functions, would be this one. If f is continuous at b, and this is read the limit as x approaches a of g of x is equal to b, this would be then the limit of the composition of the functions as x approaches a is equal to f of b. Okay, in other words, what's important about this particular theorem, it treats the continuity of a composition of functions. And so if a function is continuous at g, and g of x is equal to some output for which f of x is continuous at, then we can basically evaluate the limit by bringing the limit operator inside of parentheses. So this is somewhat unique here. I'm not going to prove this, but I'll show you an example of how this works. So note how we take this limit operator and we pull it inside the argument to the f, to the outer function. Evaluate its limit, and then evaluate the function at the limit. Okay. So for instance, an example of how you would expect this to work would be, say, consider this problem. So we're basically dealing with limits of compositions, or continuity of compositions of functions. In this case, it's a limit problem. So the arcsine function. Okay, so I trust that you remember what the arcsine function, what its graph looks like. If not, look at the Chapter 1, Lecture 1, Part 1 notes. We sketched a graph of the function. All right, so here we have arcsine composed with this function, this rational function. Okay, now, well, I guess it would be useful, I guess, if we went back and revisited the graph of the arcsine. So let me pull up a graph of the arcsine to assist with the discussion here. So bear with me. I'm going to my trigonometry notes to pull up a graph. Where did it go? Let's see if I can paste it here. Okay, good. So I was able to pull it. Okay, so here's a graph of the arcsine function as shown here. Okay, so we're interested in the limit as x approaches 1. Now note that based on the sketch of the graph, the arcsine function is left continuous at x equals 1 because x equals 1 is an endpoint. As you can see from the graph, x equals 1 is an endpoint, and we see that left continuity is present in the graph. So we can surmise that the arcsine function is continuous at x equals 1 by the fact that it's left continuous at x equals 1 and x equals 1 is an endpoint. Now if x equals 1 were not an endpoint, in other words, if the function did something like this, okay, which it doesn't, then it would not be continuous at x equals 1. Okay, so the limit as x equals 1 is the fact that the arcsine function is left continuous allows us, the left continuity allows us to pull in the limit operator into the argument. Okay, so we can use, so that's a subtlety of the theorem, which isn't very well explained. The theorem doesn't mention anything about left nor right continuity, but we presume that left continuity at an endpoint is implicitly continuous. Okay, so owing to that fact, we have an implicitly continuous understanding of the arcsine function. We can pull in the limit operator based on the theorem because we have a composition. So okay, and then that raises the next question, can we evaluate this limit? Okay, now obviously 1 is not in the domain of this function. Okay, but we need to take a secondary look at this function. If we were to use direct substitution, we would have a 0 over 0 case. So, but via direct substitution, we actually happen to discover that this function is indeterminate at x equals 1. And as I mentioned in passing a couple of lectures ago, that if after direct substitution you have an indeterminate form for a rational function, then there's a very significant possibility that the limit does exist and evaluates to a number. So one of the things we can do is we can factor the denominator of this function. So as an aside, let's do that. So we have the limit as x approaches 1 of 1 minus the square root of x over 1 minus x. Yeah, it looks like you can't factor the denominator, but in fact you can. You can factor it into a difference of 2 squares. And the reason why you want to do that is that you could achieve a cancellation of the numerator with the factor in the denominator, and that would allow you to use direct substitution with the resulting rational function. So, in fact, if we were to factor the denominator as like so, and convince yourself that this is the factorization of the denominator, then you can see we have a cancellation effect. And the signature of that was owing to the fact that after direct substitution, we had an indeterminate result. So you can see these factors cancel out, and so this would be and then now we can use direct substitution and say that the limit is a half. Okay, so the limit in parentheses is a half, so all we need to do now is figure out what the arcsine of a half is. So we can read that from the graph. Or if you have a good understanding of trig functions, you can probably figure it out without any tools or assists. So at a half, basically the sign of what number equals to a half, and So we know that that would be what the sine of 30 degrees is a half. So that would be pi 6 radians. Okay, because this is pi halves right here, and so we're roughly 1/3 of the way, right? The 0.5 means 0.5 means 0.5 of well, you're 1/3 of the way to pi halves. So if you're 1/3 of the way to pi halves, this would be pi 6 right here, and this would be pi 4 right here. Okay. I know it's a little bit confusing. Let's not read those numbers. We'll read them as that. Okay. Okay, so arc sine of 1/2 is pi 6. So just be careful when you look at these graphs for the inverse trig functions. It can be a bit tricky to interpret sometimes. Okay. All right. So let's talk about the limits of root functions. I'll just review this again for you. So let n be an integer that's greater than 0. And this is how you would write it mathematically. Z is a set of integers. Z superscript plus is a set of positive integers. All right, and let's let the composition of f and g equal to the nth root of g of x. Okay, so we have this. And so the limit, if we have this expression, the function evaluated at the limit as x approaches a of g of x, okay, that's equal to the nth root as the limit as x approaches a of g of x. Okay, so this is basically showing you composition. So with this idea, we have essentially a limit law for the nth roots of functions. So this is kind of an investigation into the these kinds of limits. The limit as x approaches a of the nth root of g of x. Okay, that's equal to the nth root of the limit as x approaches a of g of x. So this is one of the limit laws, and we'll use this a lot as well, particularly in chapter 3. So file this away for future reference. The takeaway is we can take the limit operator and bring it inside the radical. Okay, so please keep this in mind. And that also brings up the theorem that treats the limit of or the continuity of a composition of functions. So let's deal with that. All right. All right, and that'll bring up another interesting theorem, and we'll walk through the the details of this theorem. So let me paste it for you. And this will be very important in Chapter 3, and it'll also be one of the more challenging topics of Chapter 3, and it has to do with the chain rule, which we'll talk about in that chapter as well. So, all right, so let's talk about this theorem. If G is continuous at A and F is continuous at G of A, then the composition F of G of X is continuous at A. So what this means is a continuous function of a continuous function is continuous. So think of it in the way I've got it written here, right here. A continuous function of a continuous function is continuous. In other words, we have continuity for a composition. And here's kind of an informal proof, all right, of this theorem. So since G is continuous at A, we have the limit as X approaches A of G of X equals G of A. And why is this true? We'll go back to the beginning of this lecture. This is simply the definition of continuity. So the definition of a continuity, sometimes students get a little bit trapped by this idea. This is the formula for continuity. Okay, so if G is continuous, then we have a formula. So write the formula for the continuity. So if we let G of A equal to B, okay, we have F is continuous at B, which is equal to G of A. All right, so by this theorem, okay, we have, okay, so here we're taking the limit of the composition, okay. We can take the limit operator inside because F is continuous at, because F is continuous at G of A, okay. So we get this, and then what I do is I define this function h of x, which is merely the composition. It's continuous at A. Okay, so that's it in a nutshell. That's kind of how we prove. We use the limit laws essentially to show that continuity of compositions is continuous. Yeah, so we're using limits to show continuity. Okay, so an example of how we can demonstrate this. So this, yeah, that comes from the limit laws of compositions. All right. Okay, so consider this function, f of x is equal to the natural log of 1 plus cosine x. All right, and clearly the function is not continuous when the argument of this function equals to 0. So f of x, f is not continuous at 1 plus cosine x equals to 0, or 1 plus cosine x is less than or equal to 0. Okay? All right, so that means, so where does, well, why don't we simplify the response here, and why don't we just say 1 plus cosine x equals to 0. Because 1 plus cosine x is always greater than or equal to 0, right? Okay, so let me explain. Can 1 plus cosine x ever be less than 0? No, it cannot be. Why is that? Because the least value of cosine x is -1, and -1 plus 1 is 0, and 0 is never strictly less than 0. So it doesn't make sense to write this. Okay, so we can just go ahead and say equals to 0. So sometimes you have to think about the properties. Okay, so that means not continuous at cosine x equals to what? -1. And so where does cosine x equal to -1? Well, that happens at what? Odd multiples of pi. Okay, so that implies that x such that x cannot equal to odd multiples of pi. And if you're not sure where I get these numbers from, you can go back and look at my trig website and see where cosine x is equal to -1, and that happens at all odd multiples of pi. Okay, all right, good. Okay, so I want to bring up a smattering of ideas. I want to mention something that you may have picked up in algebra, and that is the intermediate value theorem. Okay, so I'm going to kind of jump to a topic here that seems a little bit discontinuous insofar as the lecture flow goes, but nevertheless, this is an important concept I need to disclose because we will use this quite a bit. Oh, yeah. Oh, before I proceed, something interesting that I forgot to give you the graph of the function before I go on. Sorry, I just saw that in my notes. Let me go ahead and portray it for you. Let me go back to that example we just did. Okay, so let's go back. Here's the graph of the function. This is the graph of the natural log of 1 plus cosine x. And later on when we go into chapter 4, we'll actually be able to sketch the graph of this function without any calculators. I'll show you how it's actually quite easy to sketch. But as you can see, well, to some extent, maybe, that we have vertical asymptotes at all the odd multiples of pi right here. Okay, so all right, so let's go forward now and let's talk about the intermediate value theorem. So let me go to the page 7. Okay, and let me go ahead and just as a review from algebra. Bear with me while I grab the graphic. Okay, so let's talk about the intermediate value function. All right, suppose that f is continuous on the closed interval AB. Okay, and so here I've sketched the blue graph right here in this illustration is my function f, and you see I've got a and b, and you can tell graphically that it's continuous on the interval a to b. All right, so we're continuous right here, a to b. Okay, now so recall from algebra, let n be any number between the output at A and the output at B. So here's my n. Okay, so see how n is between f of A and f of B on the y-axis. And we also have f of A is not equal to f of B. So what the intermediate value theorem says, and hereafter I'll refer to it as IVT, intermediate value theorem, says that there's a number c right here on the open interval, now excluding the endpoints, such that f of c is equal to n, which is kind of a remarkable fact, right? So I can find a number between A and B exclusive so that when I plug it in to my function, I'll get some output n. Okay, so f of c is equal to n. Kind of makes kind of sense. Okay, now if I choose n between f of a and f of b, it's possible that the line, okay, so here we have the line y equals n, intersects f of x at more than one point. In this case, it intersects at 3 points. So with that, the takeaway is that we could have multiple values of x that fulfill the criteria of the intermediate value theorem. Okay, so if I choose some number between f of a and f of b, okay, for a continuous function on the closed interval a to b, then there exists at least one number on the open interval a to b, such that when I plug that one number into the function, I'll get n. Okay, so a very useful result. In particular, it's useful for finding zeros of functions or explaining the presence of roots of functions. Okay, so for example, let me pull it up if I can. Okay. Show that there is a root of the equation for y equals 4x cubed minus 6x squared plus 3x minus 2. All right, so we can use the intermediate value theorem to demonstrate this. If x equals 1, okay, what is y? Y would equal to what? 4 minus 6, which is negative 2, negative 2 plus 3, which is 1. 1 minus 2 is negative 1. So assuming I did this right, x equals 1, the output is 1. How about at x equals, say, 2? So at x equals 2, y would equal to what? 32 minus 24, which is 8. 8 plus 6, which is 14. 14 minus 2 is 12. So maybe I'm guessing 12. So as you can see, what's going on with this function, if I let this be my x-axis, all right, and so if I plot 1 here, and if I plot 2 here, then I know my output at x equals 1 is below the x-axis, namely negative 1. And my output at x equals 2 is above the x-axis, namely y equals 12. And now, the subtle point about this is that y is a polynomial. And what do we know about continuity of polynomials? Well, for every value of x between 1 and 2, the polynomial exists. There are no discontinuities in polynomials. So it's continuous on the open interval 1 to 2. So in other words, y could do something like this. Okay, perhaps. Maybe, maybe not. You can use the online calculator to sketch the graph. But the fact is that as we advance from x equals 1 to x equals 2, for this continuous polynomial function, we have to cross the x-axis at least once to get there. to get to our destination. And so every time we intersect the x-axis, that is essentially a root for the function. Okay, so by the intermediate value theorem, y has at least one root. Okay. All right, so that is it for Lecture 2, Part 5. So I'm hoping that you're continuing on with your web assignments for Chapter 2, as well as I'm hoping that you're undertaking the work on your Chapter 2 project. So let me know if you have questions, okay, and start lecture number 2 next. That is, we'll start Lecture 2, Section 6 next.